Hey there, class. Welcome back. This is a short little segment in the Sensation and Perception chapter on how do we see. So I wanted to share a little story with you from the book The Brain, again by David Eagleman. He tells about this guy named Mike May, who lost his sight at age 3.5 in a chemical explosion, and the explosion scarred his corneas, so his eyes could not detect photons. Now he'd had 3.5 years of using his eyes normally, and so he had been able to see, but then at 3.5, no more vision. And so he eventually, though, became a businessman, a very successful businessman, and a champion Paralympic skier, if you can believe that, and he did that by using sound markers. As you know, other areas of the brain will compensate, and so his hearing began to compensate for the lack of vision. In his 40s, a surgery became available that allowed him to have his corneas repaired, and the surgery was in fact successful. His eyes could detect photons at this point. However, this is the point. The visual system is not a camera. You can't just turn on the photoreceptors and suddenly you can see faces and slopes and skis and trees and all of those things and understand and interpret them. Sensation is not the same as perception. So even 15 years later after his surgery, reading books was still quite difficult, and reading facial expressions was also quite difficult. So he still continued to use his other senses to gather more information, just as we did when we were children and our senses were kind of building. So after that surgery, he could see colors, he could see motion and some simple two-dimensional shapes, but he was really incapable of more complex visual processing. There's some really interesting research on kittens. It's kind of terrible, but they'll take newborn kittens when their eyes are still closed when they're newborn. I don't remember how long they stay closed naturally, but they would sew the eyes shut. And so the kittens would grow up blind, and at some point they would open up the eyes. So you would know that the eye was born normally and would be able to see, but the kitten had lacked the experience of seeing things while it moved, and so it was never able to judge depth. So you can see up here that Mike could see some simple two-dimensional shapes, but more than that in 3 dimensions was quite difficult for him. So key to remember, the eye is not a camera. Our experience tells us what to make of all that visual information that we're taking in. So vision begins when light enters the eye, and human photoreceptors are sensitive to certain wavelengths of light energy, and we call this the visible spectrum. Notice how tiny the visible spectrum is. So you know the rainbow, red, orange, yellow, green, blue, purple, or violet. This is the small amount that we can see. Now, some animals can see infrared, and of course there are other types of waves that are out there, but this is all that we detect with the photoreceptors in our eyes. So let's talk a little bit about the structure of the eye, and I want you to try to remember some of these terms for the exam. And I'll try to give you some hints, some visualizations that I use to help me remember. So the sclera is this white part of the eye. That's the part of the eye that provides protection and structure. The cornea is the clear membrane that covers the front of the eye. It does most of the focusing of the image. So here's the cornea, okay, right there. The iris is the pigmented muscle. That's this part right here that gives the eye its color. It regulates the size of the pupil. This is the pupil. The pupil is actually a hole. You actually have a hole in your eye. It's a good thing you have a cornea, right? Otherwise, when somebody kicks sand in your face, or maybe you go to Lubbock and you're in the middle of a sandstorm, you don't want to have grains of sand going in your eye, and they would otherwise. So that is, in fact, a hole that lets the light in, but the cornea covers it. I tend to remember the sclera. When a student one time said to me, they remember the sclera like sclera scary. Whenever you see scary pictures, sometimes it'll be like the white of the eye with an X or something. So that's the sclera scary part. The iris, think of that as a flower. So you look at that colorful part, it's like like an iris flower. And then the pupil, you might think that this looks like the heads of your students as they're bent down over their desk, and you can just see the top of their head. So those are just some little tricks that I use for my own memory. The lens is this part right here. This is a part that changes shape. It's convex, so it's bending outward, and it focuses the image on the retina back there. The lens has to accommodate in order to focus on a specific object. As you get a little bit older, you will begin to feel the lens stretching and moving because it becomes more stiff. So, you know, right now I do a lot of close-up work. I read all the time. I'm constantly working on a computer, and so I'm constantly focusing on things that are close to me. And if I'm doing that for a really long time and then I look far away, I will actually feel my lens feeling a little bit stiff and moving. And that's partly because I spend so much time focused close, and it's partly because I'm older. So you might just experiment and see if you notice that with your own self. Now, I will say this is a bit of a trick. We are living in an age when we are looking at a lot of close-up things all the time because we read and use devices. But that wasn't how we were for most of the millennia that humans have been around. Most of the time, we were constantly focusing on the distance, at least as much as on things close to us. We were regularly looking back and forth. So children, I tend to tell my children to take time to get outside and look at the horizon, and that'll help to keep that lens a little bit more flexible. So back here is the retina. That contains two types of photoreceptors, rods and cones. I'll show you a picture of that in just a minute. This is the part that does the transduction. So this is where you transduce the photons into electrical and chemical signals that the brain can understand. Back here is the optic nerve. The retina, you may have heard of retinal detachment. That's when this becomes loose, and that is an emergency situation. All right, so rods and cones. So the retina is that thin light-sensitive membrane at the back of the eye, and it contains all of the sensory receptors, and that's what these are. And so these sort of yellow-green chartreuse ones are the rods, and these that are a little bit more pointed are the cones. So these are exposed to light, and then they undergo chemical reactions that result in neural signals. So the cones, that's these, think of it as cones for color. You know, during the day we can see lots of colors. Now think back to the last time you were walking around your house or your apartment at night. No color, right? Very, very little color. So during the day, we use our cones and we can see color. And these are the ones that we use during the day. Most of them are located in the center of the retina. So right back here. And they're responsible for color vision, and they're active in the daylight. The rods, on the other hand, are sensitive to black and white images, and we use them at night. And they're located in the periphery of the eye. Okay? So what this tells us, this is very interesting, at night, if you're having trouble seeing something, don't pull it close to your face and try to look at it closely straight on. Instead, turn your head and look at it out of your peripheral vision, because that's where your black and white rods are, and that will actually help you to see better. Normally, if we want to focus on something, we put it right in front of us, but instead, if it's night, what you want to do is look at it from your periphery. The rods have relatively poor acuity, right? Think about it at night, everything looks a little bit blurry, you can't see all the details. And it takes about 30 minutes or so for us to adapt to the lowest light levels. So when, let's say, it's daytime, maybe you were out in the living room and it's 8 o'clock at night and it's dark in the rest of the house, but you had lights on. When you first go in the bedroom where it's pitch dark, you can't see anything. But very quickly, within a few minutes, your eyes will begin to adjust. But it does take about 30 minutes total to adapt completely. All right, blind spot. So this is kind of fun. I'm going to put a handout in your Canvas module for you to do the blind spot test. So I'm forgetting the directions off the top of my head. I think it's that you close this eye, you close one eye, and then you focus on, I think it's the plus. And then you move that paper forward and back until this disappears. It's one of those two. So look at the directions and see what it says. Oh, there it is. So yeah, there's a little bit about it. So at some point as you're moving that forward and backward, it's probably going to be about a foot from your face. One of those is going to disappear. So why does it disappear? Why do you have a blind spot? That's because that's where the optic disc is. That's where the ganglion nerve cells leave the retina. That's where your optic nerve is. And there are no photoreceptors in your optic nerve. Now, why do we not see a blind spot when we're just walking around during the day? That's because the brain fills in the blind spot with the surrounding patterns. So see if you can see your blind spot and see what happens. Oh, here's the directions. Good. So sit with your nose pointing in between the cross and the black circle. So your nose is pointing right here. And cover your left eye and stare at the cross with your right eye. So cover the left eye, stare at the cross with the right eye. Then slowly move it toward you while still staring at the cross with your left eye. And at some point, this dot is going to disappear. So give that a shot. Let us know. I think I might put something in Canvas to see how that goes for you. All right. So now we want to think a little bit about color vision. Why do we see colors? Why do we see some weird things with colors? There's some things we have to explain, right? So here's an example. Is anybody here colorblind? Why would that be? Why would red and green be the colors that we tend to be blind to? Why would it not be blue, yellow, or black and white? Why is it red, green? Have you ever been not really looking at something particularly, but you're kind of spacing off, but something's in your vision, maybe a picture. So you can see like a dark picture frame and then the white of the mat, and maybe it's a light colored picture. And then you close your eyes, and what do you see? You see that image reversed. You see a white frame with black in the middle. Why is that? So there are two different approaches to thinking about how we see color. The first is opponent process theory. This is the idea that color vision is the product of opposing pairs of color receptors. This generates three systems: red, green, blue, yellow, and black and white. So when one member of a color pair is stimulated, the other member is inhibited. So we have a blue circle that's stimulating your blue color receptor, and that would make yellow recede. Okay, the other one is inhibited. This explains after images and color blindness. So here's what I want you to do. I want you to stare at this dot for, I don't know, a minute. Yeah, probably a minute. Go ahead and pause the video and stare at the dot for 1 minute. Don't look at anything else. And then as soon as the minute is up, I want you to turn your head and look at a blank wall, preferably a light colored blank wall. Okay, go ahead and pause the video and I'll see you in a minute. Okay, hopefully you're back. Hopefully you did it. If you didn't, you missed out. What you should have seen, maybe I won't say it in the video. You would have seen something very interesting. You would have seen an actual American flag with the correct colors. Yellow would have appeared blue. Green would have appeared red. Black would have appeared white. So this is a screwed up American flag, but if you stare at that for a minute and then look at a blank wall, you're going to see an after image of the correct American flag. This seems to provide some support for opponent process theory that we have these pairs of colors, and if green and black and yellow are stimulated, then red, white, and blue are suppressed, and they will pop back up as soon as we stop looking at this thing. Okay, I hope you did it. So, hope you enjoyed that little segment on vision. There's more in your textbook, but there's only so much time. I'd rather go a little bit more in depth than go a little bit more broad than go too much in depth. So I will see you in the next video for How Do We Hear?